Hello and welcome. Now we will be discussing about counting sort. Right? We have moved through heap sort to something completely different. Like heap sort was clever, but it was still a comparison-based sort. So it still had that O in log n barrier. But what if I told you that we can sort faster than in log n? We can so what if I told you that under the right condition we can sort in linear time, which is ON. That's exactly what counting sort allows us to do, and it does it in a way that's almost magical. Instead of comparing numbers, we count them. Let me start with a fundamental question that drives everything where we are about to learn. Can we sort faster than n log n? Right? Yes, but there's a catch. We can sort faster, but only if we know something about the data beforehand, right? Specifically, we need to know the range of values that we are sorting. Think about it this way. Imagine you are a teacher and with a stack of 1,000 exam papers, and each paper has a score between 0 and 100. How would you sort them? A comparison based sort like quick sort would compare scores against each other. It would take about around 10,000 comparisons. That's fine, but if I have showed you a faster way, what if instead of comparing scores, you just created a tally sheets with 101 slots and one for each possible score from 0 to 100. Then you can go through all 1,000 papers and put a tally mark in that slot corresponding to the each score. After you have gone through all these papers, you just read the tally marks in order, right? That you have your sorted list. So that's exactly what counting sort does, right? So it's instead of comparing numbers, we count them. Now let me be very clear about the conditions. The data consists of integers, and we know the range of values, minimum and the maximum. The range is relatively small compared to the number of elements, right? And when these conditions are met, counting sort achieves n plus k time, right? So complexity becomes O n plus k time, where n is the number of elements and k is the range of values. So when k is small, this is essentially O n linear time, right? So why counting sort is different? Let me emphasize why it is why it gives such a big deal. All sorts learned before: bubble sort, selection sort, insertion sort, merge sort, quick sort, and even heap sort. They all work by comparing elements. They ask questions like, is A greater than B, and make decision based on answers. But counting sort doesn't ask that question at all. It never compares two elements. Instead, it uses the values themselves as integers into an array. This is only possible because the values are integers within known range, right? So counting sort a specific sequence of steps. I am going to work through each one carefully. First, it finds the range. We need to determine the maximum and minimum values in an input array. Why? Because we need to create a count array that's large enough to hold counts for all possible values, right? The size of the count array is max minus min plus 1, right? We use the minimum value to shift the values so that they become valid indices. And then we create the count array, and we create the array of size range initialized to all zeros. This array will store the count of each value. Think of it as a tally sheet with one slot for each possible value, and then we count the counting of occurrences, right? Then we compute cumulative counts and we build the output array. So here you can see in the example count 0, 1, 2, 3 and so on, right? We define the range, right? So here how many times 82 appears? It appears 3 times, right? So we input 3 here. How many times 76 appears? It appears 1, 2 and 3, right? How many times 65 appears? It appears 1 time, right? So how many times 0 appears? There's no 0 in the array, so we keep it as 0, right? Okay, then what we do? We cumulatively, so what's the smallest element here? 65, right? So what should we do to get the cumulative count? We have to add the previous counts, right? So previous counts are all 0. What we get value initially was 65, right? All the indexes below 65 are count as 0. Okay, so there is no lesser value than 65 here, right? So we have 65 as the cumulative count is 1 itself, okay, because these are all 0. 1 plus 0 plus 0 plus 0 and so on. This is 1, right? And when we go to 66, we get the previous sums, right? So 66 here we have 0, these are zeros and this is 1, so totally we have 1 as the count, okay? Then when we go to 76, we have 3 here, right? So if we add all together, what is the cumulative count? 3 plus 4 plus all the zeros, we have the 4 as the count, okay? And then we have 77, right? 0 plus 3 plus 1 plus all zeros, we have 4, right? Likewise we get the cumulative count. That's it. So now let's look at counting sort full example, right? Here we have the input arrays 4, 2, 2, 8, 3, 3, 1, right? So unlike in bubble sort or merge sort, counting sort does not compare numbers with each other. Instead, it simply asks how many times does each number appear, okay? So step 1 is to count the occurrences. First, we look at the range of numbers, right? The smallest number is 1 here, right? And the largest number is 8, right? So we create a counting array for values between 0 to 8, and initially we need to set every count to 0, right? So now we scan the input one element at a time, okay? So first element is 4, right? So increases the count for 4, right? Here we have 1, okay? Initially we have 0 here, now we have 1, okay? Next element is 2, right? So count at index 1, right? So the second element, we need to increment the value index at 2, right? So we need to increase it by here, okay? Likewise here we have 2 again, so we need to increase the count by 1 again. So totally we have 2 here. Okay, and just like that we need to fill this count array. Okay, then what we need to do is we need to get the cumulative count, right? So how do we get the cumulative count? It's current count plus previous total, right? So we have current count as 0, and so the cumulative count is 0. Okay, and now for this one we have current count as 1 and the previous count is 0. We get as 1. For here, how do we get 3 here? We have current count as 2 and the previous count as, altogether we have 1, right? So here we have 3. Likewise we need to fill this cumulative count array also, right? After that, what we need to do? We need to place this. After that we need to do? We need to place those elements, right? So element 1 cumulative count says, so in this step 3 we need to place those elements, right? So from right, step 1 we have 1 belongs in position 1 minus 1, which is at index 0, right? So we need to input it. So we need to input it in index 0. Okay, and the second thing is we have 3 here, right? So it's at index which is at count 3, right? Count 3, 0, 1, 2, 3, right? Sorry, count 3, right? Yeah, count 3. This is the reference, right? Count 3, which is 5, right? So the position index is 4. We need to place 3 in 4th position, right? And then the next thing is 3, right? Okay, here we get the elements from right. Okay, and we get 3 here, count, then we get 3 here from this. Okay, and count at 3, which is the value. What's the value? Count at 3, we have cumulative count. Before we have 4, right? So the position is index is 4 minus 1 and it's equal to 3, right? So we place 3 here, right? And what we do, we need to decrement the cumulative counts in each step, right? Okay, likewise we need to fill this table, right? Here we have count 3 as 5 from this, right? So how do we get 5 here? From this. Okay, after decrementing we get the 4 here. Okay, so once the value appears twice, you need to decrement the cumulative count. Okay, that's what does this in this column, right? So practice by your own example and place it in this table and you will understand, right? key takeaways are: count how many times each value appears, and convert counts into cumulative counts, and traverse the original array from left to right and place the each element at cumulative count -1, and then decrease the count by 1. Okay, so just remember these steps, right? So this is the pseudocode for counting sort, right? So we need to find the maximum value, minimum value, and the range, and then we need to create the count array and the number of counting occurrences for each value, and then we need to get the cumulative counts, and then we need to get the output array, right? So just remember these steps and solve those examples, right? So the time complexity becomes O n plus k, right? And space complexity becomes OK, and it's stable. You can see because of this we use counting sort, and it's popular, right? And it's in place, no, right? So the advantages, we can say this is the biggest advantage: counting sort can sort in O n time, which is faster than any comparison based sort, right? And which is stable sort. This make it useful for multi-key sorting and other applications where stability matters, right? And it's also simple. The algorithm is straightforward and easy to understand, and it's also predictable performance. And when we look at disadvantages, it's work only for integers, right? So you can't use counting sort directly on floating point numbers, strings, or any other integer data types, right? And it requires large memory for large ranges. If the range k is large, the count array becomes impractically large. For example, if you are sorting from 1 to 1 million, you need to count array of size 1 million, even if you only have 100 elements to sort, right? And not suitable for floating point numbers. If you need to scale and shift floating point numbers into integers, which adds complexity and may lose precision. Okay, and the next disadvantage, we can say not an in-place algorithm. Okay, it requires extra space for output array and count array, and also we can say you need to know the minimum and maximum values to create the count array. Okay, so when to use counting sort? For example, these are use cases. Exam marks, you have thousands of students, but the score ranges is from 0 to 100. So k equals 101, 101, which is small, and n is large. So counting sort gives you an O in time complexity, right? And for example, in ages in population, we can say it around the range 0 to 150, and so the k equals 151. So we can compare n, right? And also we can have grades A, B, C, D, F, and assign values like to those map grades, and so we can have any integer with small range. If you are sorting integer values and the difference between maximum and minimum is small, counting sort is the best choice. Okay, and also the counting sort, when not in use, when this range is large, if k is more than n, the sort becomes wasteful. For example, sorting 100 numbers that range from 1 to 1 million would require counting array of size 1 million, so which is inefficient. right? So when the data is not an integer, you can't use, and also when the memory is limited, and when you need an in place sort, so you can't use, right?